Okay, I think this is the last thing I'm going to make you do today, so go ahead and get excited. I don't even know if I'll give you extra practice with this. We'll see. So we've just established that there are 180 degrees in a triangle. And actually, this is a really powerful statement in geometry. The fact that there are 180 degrees in a triangle and we can concretely prove it by lining up the angles of any triangle in a straight angle is a very, very, very powerful concept that's used in geometry to determine the angle measurements in any other polygon. So now we're going to look at how we can use this fact to determine the number of degrees in any polygon. So you'll look at these polygons here, right? 1, 2, 3, 4, 5. There's 5 sides, so there's a pentagon here. It is an irregular pentagon. It is not a regular pentagon. Its angles are all different measurements, and the side lengths are all different measurements. But notice what we've done. We can separate any pentagon into triangular regions. So you'll see these dotted lines coming from one corner here. So the important thing is that it has to come from one of the vertices. Okay, so I pick one vertice and then I draw a line to every other vertice, right? And clearly these are already drawn, right? You don't have to do that. So, and I could do this from any corner. It doesn't matter. So I could go from there and I could go from there to there, right? But let's look at what happens here. When I draw these triangles, look at what happens. Okay, we know there's 180 degrees in this triangle right here. Okay, so these three angles add up to 180, right? And then we know there's 180 degrees in this triangle right here. So these three angles add up to 180. And then we know there's 180 degrees in this triangle right here. So these three angles add up to 180. Well, notice that what we've just done is by making all of these triangles, we have figured out the degrees for every angle here. Notice that this purple line covers this angle of the pentagon. The red and purple line cover this angle of the pentagon. The red and green line cover this angle of the pentagon. This green line covers this angle of the pentagon. And then these three together cover this angle of the pentagon. So by separating it into triangles, we have established all of the angles of the pentagon and their degree measures. If this is a little confusing to you, we're gonna explore this further and come up with some generalizations that we can make in looking at any pentagon or any polygon. Okay, so here what I'd like you to do is on your paper, okay, you can make this table in your notes, and then we're going to draw polygons of 4, 5, 6, 7, 8, 9, and 10 sides. And really you can do this on your own. I'm only going to do a few of them and then we'll look for a pattern. Okay, you can do all of them and find the pattern. But basically you're going to draw the polygon and then pick one vertex and draw all possible diagonals from that vertex. This is exactly what we just did a while ago, right? Picking a vertex of the shape that you draw and then drawing diagonals to every other vertex from that one vertex. Okay, make sure that you don't do, you can't pick one vertex and then draw another diagonal here. Okay, we want all the diagonals coming from one vertex. Okay, so this guy would not be allowed. It has to be triangles that we're creating. So if your shape doesn't break into triangles that are like this from that one vertex, then you are doing it incorrectly. All right, and so let's do this and let's look for some patterns. Okay, so we're going to start with 4 sides. Okay, so I'm going to draw a polygon with 4 sides. Okay, 1, 2, 3, 4, and I'm going to draw I'm going to pick a point and I'm going to draw a diagonal, and that's the only diagonal I can draw. Okay, we're not doing it from every vertice, just one vertice. Okay, so when a polygon has 4 sides, okay, the number of diagonals that we can draw is 1. Okay, let's do the diagonal for 5 sides. So 1, 2, 3, 4, 5. Okay, and now I'm going to pick a point and I'm going to draw all my diagonals. So when I have a polygon with 5 sides, the number of diagonals I can draw is 2. Okay, let's do one with 6 sides. 1, 2, 3, 4, 5, 6. Ooh, not very good, but whatever. Yours can look whatever way. I'm going to go from this point here. So 1, 2, 3. Okay, and so when I have 6 sides, I can have 3 diagonals. Okay, do you see the pattern already emerging? Okay, you can do more if you'd like, but clearly it's 1, 2, 3, 4, 5, 6, 7, right? Okay, so now with this knowledge, let's see, can we find a pattern that predicts the number of diagonals that can be drawn from one vertex in a polygon? So we want to know, can we create an equation, the pattern as a rule, that's an equation where n is the number of sides and d for the number of diagonals. And it predicts the number of diagonals. So that means that we're going to have d equals. Okay, go ahead and pause the video and see if you can come up with the rule on your own. Okay, and hopefully what you determined is that the pattern for the rule is using n for the number of sides. It is clearly n minus 3, right? This is our rule here. So when I have a polygon with 4 sides, 4 minus 3 is 1, I'll have 1 diagonal. When I have a polygon with 5 sides, 5 minus 3 is 2, I'll have 2 diagonals. When I have a polygon with 10 sides, 10 minus 3 is 7, I'll have 7 diagonals. Okay, so there we go. We've established the rule again, and notice this is actually an equation in slope-intercept form. We could graph this and have a table that would tell us the number of diagonals for any number of sides. And notice that the number of diagonals is dependent on the number of sides. Okay, so there's the collision of algebra and geometry again. Okay, now what we're going to do is I'm going to put my number of diagonals in. I'm just going to write them in. So when it was 4, we had 1, 2, 3, 4, 5, 6, 7. Okay, now we're going to count the number of regions. Okay, so this is what we're looking at now, the number of regions or the number of triangles. So let's go back and look at that. And you have yours on your paper. I'm going to go back and forth here for a minute. Okay, let me okay, it's right here. So when we have the 4-sided polygon right here, okay, when we have that, we have 1, 2, 2 triangular regions. Okay, so when we had 1 diagonal, we had 2 regions. Okay, when we had 5 sides, we have 1, 2, 3 triangles. 1, 2, 3 triangular regions. Okay, so we have 3. When we have 5 sides, 1, 2, 3, 4, 5, we have 1, 2, 3, 4 triangles. I'm sorry, and that is for 6 sides, isn't it? 6 sides and 4 triangles. All right, here's the pattern again, right? You see it 2, 3, 4. What do you think is going to be here? 5, 6, 7, 8. Okay, so now what we want to do is looking at this, we're going to find a pattern relating the number of sides, in a polygon to the number of regions formed by drawing the diagonals. This time we have n for the number of sides, so this is n, oh, beautiful n there, okay, and we have r for the number of regions, or we're really thinking about it as the number of triangles formed. Okay, so go ahead and pause and see if you can come up with that pattern on your own. Okay, and what you should have ended up seeing is that the number of regions or the number of triangles formed is found using the equation n minus 2. N minus 2, right? Essentially here we're just ignoring this row. Okay, so looking for the pattern here. So how did I get from 4 to 2? 4 minus 2. How did I get from 5 to 3? 5 minus 2. How did I get from 6 to 4? 5 minus 2. Okay, so we see that in order to figure out the number of triangles for any size polygon, we just do the number of sides minus 2. Now this is really important, so you should circle, highlight, star, whatever you want to do in your notes because this is extremely important. Okay, and so you can try that for these 4 right here if we wanted to figure out if we have a 20-sided figure, how many triangles would that break down into? So if I have we call it a 20-gon, right? Hopefully you read, I mean, there's a more formal name, but we get lazy in math, right? That's the deal. So it's a 20-gon is what we can call it once it's greater than 13. And then we would do the number of sides minus 2 gives us 18 triangular regions. That's easy, right? Okay, now think back to what we did at the very beginning. Why would we want to know about how many triangular regions there are, and how can this help us? So this will inevitably tell us the number of degrees there are in a polygon. So if we're looking at this figure here, okay, notice that we created the 3 triangles. I have 1, 2, 3 triangles here. And most importantly, that all the triangles' angles they create, or they end up being the angles of the entire polygon, right? So here, these 3 angles make up this whole angle for the pentagon. This angle makes up that whole angle for the pentagon. These 2 make up that whole angle for the pentagon. These 2 make up that entire angle, and this makes up that entire angle, right? So that's the 5 angles of the pentagon. There are no other angles that are missing there. And so if I have in a 3-sided figure, it's just a triangle, we've already determined that there are 180 degrees in a triangle. But in a quadrilateral, we have 2 triangles, right? And the 2 triangles are, when we look at it, all of the triangles' angles create the angles, because we're going from one vertice to the others, right, creates the angles, or cover all of the angles of the quadrilateral. So I have 2 triangles in there. So if we just do 2 times 180, we end up seeing that there are 360 degrees in a quadrilateral. And we know that. Everybody knows, right? When I have a square, right, it's 90 degrees, 90 degrees, 90 degrees, right? Ooh, that's rough looking. Let me change that a little bit. 90. We're trying to make squares here. 90, 90, 90. Right? Everybody knows that those are 4 90-degree angles. 90 times 4 is 360, right? Okay, so then if I have the pentagon, a 5-sided figure, we have 1, 2, 3 triangles, or you see it here, right? And we ended up doing 3 times 180. So there are 540 degrees in a pentagon. And then if I have a hexagon, there are 4 triangles, right? We do n minus 2. So we would do, for a hexagon, we have 6 sides. So n minus 2, okay? And then 6 minus 2 is 4, and then we do 4 times 180, right? Because that's 4 triangles. So there are 720 degrees in a hexagon. So this is actually in a equation, or an expression really, that we can use to determine any number of degrees in a polygon. So that is let n equal the number of side lengths of a polygon. Okay, then the expression n minus 2 times 180 gives us the number of degrees in the polygon. So let d equal the number of degrees in a polygon. Right, and so here, check this out. Here we go. It's an equation in slope-intercept form. So now we know these have a linear relationship. If we were to graph it, right, we could distribute the 180 over the n minus 2, and we would end up with the expression d equals 180 n minus 360, right? But typically we use this one right here, but I just think it's important to note the collision, or the overlapping of the geometry with the algebra here, right? So now we know there must be a linear relationship between the number of side lengths in a polygon and the number of degrees of their angle measurements, right? It's very interesting. Okay, so how can we use this information, and make sure you've got this one right here in your notes, right? This is something we'll need to know. Actually, we need to memorize and learn. Okay, how can we use this information to help us, to help us blank. Oh, I messed up here. To help us calculate the angle measurements. It should be calculate here. Calculate the angle measurements of a regular polygon. Okay, you had seen the videos or played around before, and you know hopefully that a regular polygon is a polygon in which all sides and angles are congruent. Okay, so by definition, when all the side lengths are congruent, all the angles are congruent. Okay, and so here a three-sided regular polygon is just going to be an equilateral triangle. It's got all three sides equal. Oh, let's see if I think I have, yeah, here we go. Here are my regular polygons. So here's what that looks like right there. Okay, and then we have a four-sided is clearly going to be a square, right? Five-sided is going to be a pentagon. Six-sided is a hexagon, looks like this, right? The regular octagon is like a stop sign, right? Eight-sided figure. Okay, and so here's what those figures look like. I think on the other website, the other polygon website, you could see more of what the figures would look like the nonagon and the heptagon are very interesting looking. And you can actually even see them up here, I believe. Let's see. You can see nonagon. There's 11gon, right? Decagon, dodecagon, what they look like. Isn't that interesting? And so, 1, 2, 3, 4, 5, 6. Oh, I just realized I picked the heptagon here. Sorry about that. Let me pick the right one. There we go. Hexagon, there it is. There's the hexagon. Okay. And so, same thing happens, right, when we break them down, when we go from one, like clearly I have a triangle there, but when we go from one corner here, we end up with two triangles. When we go from one corner here, we end up with three. When I go from here, we end up with four, right? It's the number of sides minus two. So 6 minus 2 is 4. 5 minus 2 is 3. 4 minus 2 is 2. 3 minus 2 is 1. Okay, and then when we multiply by 180, because there's two triangles to figure out the degree measurements. So 2 times 180 is 360. 3 triangles, 3 times 180 is 540, blah, blah, blah. So how can we use this to help us figure out what the angle measurement of one of the angles is? This has probably jumped out at a lot of you, but in case anyone is missing it, if I have, this is my pentagon, right? If I have 540 degrees total in the pentagon, right? How can I determine the measures of each angle in a regular pentagon? And now this can only be done for a regular pentagon because, why? All of the angles are congruent. So what does that mean? This x could be put in every corner, right? So algebraically, 1, 2, 3, 4, 5. 5 times x is equal to 540. And so we would just divide by 5 on both sides, right? 5 goes into 5 once, 5 goes into 40 8 times, right? And so what does that mean? That each angle measurement of a regular pentagon is 108 degrees, right? And then that's interesting because we could do this for any regular polygon. We just have to divide by the number of sides, right? Because if there's 5 sides, 1, 2, 3, 4, 5, we end up having 5 angles, 1, 2, 3, 4, 5. Okay, and so now we've created another algebraic expression or another understanding of how to calculate the angles in a regular polygon. So that would be the degree or the measure of an angle of a regular polygon. So we can just call that, we'll just call it A. Angle A of a regular polygon is equal to the number of sides minus 2, right? This tells us how many triangles there are in the polygon, times 180 tells us the total number of degrees in the polygon, all divided by n, right? The number of sides, because the number of sides is equal to the number of angles. And so this is the expression we can use to determine the angle measurement, of a regular polygon. Again, it only works for regular polygons because all of their angles are congruent, right? All of their angle measures are equal. Okay, so here is the angle measurement of a regular polygon is found that way. Now, go ahead and why don't you see if you can not find the measure of Oh yeah, find the measure of one interior angle in each regular polygon. Okay, so for each of these, figure out if they are regular polygons, right, what we were just working with. Okay, you'll just mimic what we've just done using that equation, n minus 2 times 180 over n, right, where n is the number of sides. Okay, and sometimes students don't know the vocabulary for the polygons. You do need to know, like, that a heptagon is 7 sides. You should know that. Up to a 13gon, right? You should know up to a 13gon. And so, again, the equation you're going to use is the number of sides minus 2 to figure out the number of triangles times 180 to figure out the total number of degrees in the polygon divided by the number of sides, and that'll give you each one of those. Okay, so go ahead and try that and see if you can come up with the correct answers there. And then I encourage you to look online. Just type in what is the degree measurement of a regular octagon for each angle, and you can check your answers that way. And then here is a little challenge for you. I'm going to put a website after this one that you can review that goes into this a little bit more. But we know the exterior angles of a polygon. Okay, an exterior angle of a polygon is just 1, 2, 3, 4, and 5. Essentially what it is if I extended this line segment for the polygon, the angles that form linear pairs with the polygon are the exterior angles. So notice the interior angle, these are the interior angles, the angles on the inside of the polygon, interior, inside, okay, interior. The is like the inside of the polygon, okay? The exterior angles, again, is if we extended this line of the polygon, it's the angles that create a linear pair. So notice there are linear pairs with the interior angles. See the linear pairs that are formed with the interior of the angles there? So for example, this right here would not be an exterior angle of the polygon even though it's on the outside. Exterior means outside. Okay, I'm sure you've learned exo is out. It has to be an angle that's forming a linear pair, and each interior angle actually forms 2 linear pairs. So if we take a look here, I could extend this line the opposite way. And so this angle right here forms a linear pair, so that is the exterior angle. And notice it's a vertical angle with angle 5, so the exterior angles are congruent. But what we see is when we add up the exterior angles of a polygon, they always equal 360 for any polygon. What a powerful statement. So here if I add up this angle plus this angle plus this angle plus this angle plus this angle, it adds up to 360. And this is the case for any polygon. So here we have, this is going to be 60, 40, 40, right? Because they make linear pairs, right? So that's how I'm calculating it. 180 minus 120 is 60. 180 minus 140 is 40. 180 minus 100 is 80. So notice we have 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? 180 degrees in the triangle, right? Which is the requirement. When we look at these exterior angles, the ones that make the linear pairs, right? Linear pair. When we add those up, they equal 360. Same thing happens when I have a quadrilateral. When we add them up, they make 360. So how can we use this information to help us determine the angle measurements of regular polygons in a quicker way? So how could this information help me figure out the angle measurement of a regular pentagon in an even quicker way than the expression we just created? If you figure it out, you can go ahead and try it out with these 3 again and see if you get the same answer. Okay, again, the next website that I'll post is just extra if you want to do it. It does actually go over the answer for how to do this, and it reviews this in depth, more in depth. So if you're having trouble with this or with the expressions that we just created, you can review that. But it's just extra. You don't have to do it. And I think I might just give a little quiz warm-up or something on this to make sure that everyone's covered it instead of giving you extra work right now. Thanks for working on a snow day, and I hope I get to see you tomorrow, but if I don't, look up here again for your next set of activities to do tomorrow. Thanks. Miss you guys. Bye.